Hey guys, in this video we're going to be taking a look at this particular integral, the integral between 0 and 1 of x to the negative x dx. Now this here is known as pretty much the sophomore's dream, this particular integral. It's a very famous integral, but it's actually very hard to evaluate. The reason why is because of this term up here, x to the power of x. Now this alone is very hard to differentiate, but we can take advantage of this using a log property or slash an exponential property. We can rewrite this because we know if we have e to the power of log of a, that's the same as just a, because those terms cancel out, because ln is log base e, and then if you have e to the log base e of a, those cancel out because they're like inverses of each other. So if we have that situation there, we just rewrite it in terms of an exponential slash logarithmic term. So this would be e to the power of natural log of x to the power of negative x. And then from there, you bring this down the front here, because you can do that using log laws. Because, for example, if you had log of x squared, you can bring that 2 down the front there and go 2 natural log of 2. Natural log of x, sorry. Works with any base, but we'll just use ln in this case here. So we're going to do a similar thing to this in here when we integrate. Now if you're differentiating, you would use the chain rule slash product rule here, but integrating, we're just going to change how it looks pretty much. So this will still be the integral between 0 and 1, and we're just going to rewrite this function here as e to the power of log of x to the negative x dx. Then, like I said before, you can bring that down the front and then rewrite it like this. The integral between 0 and 1 of e to the negative x natural log of x. Okay? Once you've written it like that, it's pretty easy to start making substitutions. But before we make any substitution, we're going to rewrite our Euler term in terms of a Taylor series. So a Taylor series is pretty much approximating a function using an infinite polynomial. So the Taylor series of e to the x is the infinite sum, the discrete sum from n equals 0 to infinity of x to the n on n factorial. You'll more commonly see it written like 1 plus x squared on 2 factorial, and then that goes on forever, pretty much. All we're going to do is rewrite this entire term here in terms of an infinite sum. So what I mean by that is if e to the x is this, that means e to the negative x natural log of x must be this, the infinite sum, just the discrete one, from n equals 0, so that's a better way to write it, n equals 0 to infinity, and then you just replace wherever the x is with this term here, so it'll be negative x natural log of x to the power of n, all on n factorial. Okay, that's written a bit funny. N factorial. So we can rewrite our integral just using this. So the integral of 0 to 1 of e to the negative log and e to the negative x natural log of x dx can be written like this. The integral between 0 and 1 of the infinite discrete sum from 0 to infinity of x, negative x, natural log of x to the power of n on n factorial dx. Now n is a function, it's part of our index with our infinite sum. Now what we can actually do here to make things a bit easier is we can actually interchange the sum and the integral. The reason why is because of the uniform convergence of this sum, so we're allowed to do that. If you want any more information about that, just Google uniform convergence of a sum, and hopefully some video will come up explaining why you can interchange these when you've got a uniform conversion of a particular sum. Because you can't always switch the integral and the discrete sum, but in this situation you can. So we can rewrite it as the infinite sum from n equals 0 to infinity of the integral between 0 and 1 of negative x natural log of x all to the power of n on n factorial dx. Now I actually am going to change how this looks as well. I'm going to apply my exponential laws to all these, so I can rewrite this as still the infinite sum from n equals 0 to infinity, the integral from 0 to 1 of Now I'm going to keep the negative sign with the log x because I'll cancel that out eventually when I do a u sub. So I'll write it as negative natural log of x all to the power of n and then x to the power of n on n factorial dx. Now I've finally got something like this, and it looks very complicated at the moment, but we're going to break it down, okay? So all I'm going to do is do a u substitution. I'm going to let u equal natural log of x, well, negative natural log of x. So let u equal negative natural log of x. Now I'm going to change my bounds. So when x equals 1, u will be negative log of 1. Natural log of 1 is 0, so u is just going to be 0. When x equals 0, u is going to be natural log of 0. Now you can't evaluate log of 0 because it's undefined, but it approaches negative infinity. So what we can do is pretty much replace this here with just negative infinity because it approaches it pretty much when you get close to 0. So u equals negative of negative infinity, which is just positive infinity. Okay, so that's your change of bounds. Now what I'm going to do is find du dx, because if I make this substitution now, I'll have u and I'll have x's and I'll have dx's. I want to convert everything in terms of u. So that means I want to rewrite this x here in terms of u. So I will rewrite it like this. So negative u equals natural log of x. I know natural log is log base e, so I can rewrite this in terms of an exponential form. So that one will be e to the negative u is equal to x. So that's going to be important very shortly. And now I need to find a du dx. So I'm going to differentiate this with respect to x on both sides. So I'll have du dx equals the differential of natural log of x is 1 over x, so it'll be negative 1 on x. Now you want dx as the subject, so multiply both sides by negative x. So I'll have negative x du dx is equal to 1. Then multiply both sides by dx, so you have negative x du is equal to dx. Okay, so now that we've got that, there's one last thing we're going to do. We don't want x's, we're just going to replace this guy with this guy here. So I can rewrite that as negative e to the negative u du is equal to dx. Holy dooly, that was a mouthful, but we got there in the end, didn't we? So using this, using that, and using our change of bounds, we can rewrite this. So all I'm going to do is just copy this, because I'm very lazy, I'm not going to write it again. Copy, and rewrite this entire thing. So when this undergoes a u substitution, this turns into this. Still the infinite sum. That's a interesting looking sum. I can rewrite that a bit better maybe. And we'll go with that one. It's from n equals 0 to infinity of the integral. Now, when x was 0, we said that was infinity, so infinity. When x was 1, we said that was 0, so that's 0. This here turns into u to the n. This term here, we know x is equal to this here. So what we have is e to the negative u all to the n, divided still by n factorial. And then dx, we literally just wrote here, is negative e to the negative u du. Okay, now we can change how a lot of this looks at the moment, because we can apply exponential laws here. So we can rewrite that. We've got this negative sign here, so we can actually bring that out the front as well. So if I am lazy and copy this again, copy, place that there. The reason why I'm going to bring the negative out the front is because I can move my infinity and my 0 around by putting a negative sign out the front. So if I bring that negative out the front and then flip my bounds, I'll still have a positive integral. So of the sum from n equals 0 to infinity of the integral between 0 and infinity. So this negative is gone and these bounds are switched, because if you had the integral from a to b, that's the same as the negative integral from b to a. So all I've done is applied that and cancelled this negative as well. So I'll have u to the n. I can rewrite this using exponential laws. So it'll be e to the negative un, all on n factorial, multiplied by e to the negative u du. Righto, so we're getting there very slowly. It still looks very complicated, but we're slowly getting there. We can see these have like bases, so what we can do is actually multiply them together. So I can rewrite that whole thing once I copy it again. So I can rewrite that as still the infinite sum from n equals 0 to infinity of the integral 0 to infinity of u to the n. If I multiply e to the negative un by e to the negative u, I'm going to get pretty much, what's it called? You add the indices, I'll get e to the negative un minus u, and then I can take out a factor of negative u. So I'll have e of negative u on n plus 1 in here, all over still n factorial du. Righto, so now we've got this guy here. So let's just copy that, because I'm sick of writing it out a couple times. So move that down here. Oh, I forgot the bracket. Did I forget anything else? Nope, that's all good. Righto, so we've still got something very tricky, but all we're going to do is apply one more substitution, and then a lot of this stuff is going to be very easy. So what we're going to do is, I don't like this n plus 1, and I don't like this term up here. I'm going to change it to another variable. Let v equal u of n plus 1. So that means dv du is just going to be n plus 1, pretty much. So that means dv is going to be n plus 1 du. Okay? Now that's going to be important very shortly. So that means I can rewrite this term here, u to the n, because I can remove that over there. I know u is equal to v on n plus 1. I can rewrite u to the n as v on n plus 1 all to the power of n. So that will just be vn on n plus 1 all to the power of n. And yeah, I'll leave it like that. So let's apply this substitution now. So this integral here, when we make this substitution, will, bracket, so I'll call it a v sub. The bounds won't change at all, because when u is 0, this v is still going to be 0, and when u is infinity, v will still be infinity. So the bounds stay the same. So it's still this sum, n equal from 0 to infinity, and then these bounds stay the same, 0 to infinity. And then now we replace this guy with this guy here. So what we're going to have is v on n plus 1 to the n, times still by, there's going to be an n factorial down here. Extend that bracket, not bracket, fraction, sorry. I can replace this with e to the negative v, and then dv, I need to make du the subject. So du is going to be dv on n plus 1. So I can replace this guy with this guy. So I'll have, what was it? dv on n plus 1. Okay, so just copying this and moving it down here where there's a bit more room. We've still got something very complicated, but you can see that is the same as that. So what effectively I have is n plus 1 to the n times by n plus 1. So you can see these are like terms, so you can apply your exponential laws, and this is the same as n plus 1 to the power of n plus 1. So I can rewrite that like this. That's a terrible sum, I'm very sorry. Rub that out. N equals 0 to infinity of the integral from 0 to infinity. And I pretty much have v n e to the negative v dv on n plus 1 to the power of n plus 1 on n factorial. Now what I can actually do is take the bottom half out the front, because it's independent of our variable here. So I can rewrite that again like this. So infinity n equals 0, and I have 1 over n plus 1 to the power of n plus 1 on n factorial, multiply by integral here, 0 to infinity of v, oh, not e, or you can write e first if you wanted to, but we'll write v because we've stuck with that, v to the power of n e negative v dv. And now if you can actually recognize this thing here, this here is the gamma function. So more specifically, this is gamma of n plus 1, which is n factorial. So we can actually substitute this entire integral here with just n factorial. So what we're going to get is the infinite sum of n equals 0 to infinity of 1 on n plus 1, n plus 1, n factorial times by n factorial. That whole integral is gone because it got replaced with this. That cancels, so what we get is the infinite sum, the discrete sum from n equals 0 to infinity of 1 on n plus 1, the power of n plus 1. We can actually rewrite this again because we can move the index along. So if we evaluate the first term, we'll have, let's say n equals 1. We'll have 1 on, oh not n equals 1, n equals 0. If we put in n equals 0, that'll give us your first term. So what we effectively get is 1, then we get 0 plus 1 to the 1 plus the sum of n equals 1 to infinity. Oh, hold on, I think I made a mistake there. If you're changing your index, if we move everything along by 1, then we can rewrite this as the sum of n equals 1 to infinity of 1 on n to the n, or n to the negative n with that sum involved. So our integral from 0 to 1 of x to the negative x dx is equal to the discrete sum from n equals 1 to infinity of 1 on n to the n. And that is your answer. I hope you enjoyed this video. If you have any questions about any of this, leave something in the comments and I'll try my best to answer them, okay? But anyways, I'll see you in the next video.